Hi everybody. My name is Owen Ruzanski, KD3ALT. I am a student at the University of Scranton. I'll get a little bit into who I am, where I'm from, and everything about that on the next slide. But I'm here today to talk to you about the development of the contesting and dxing dashboard to be used with the HamSCI personal space weather station. Figure out how to move next. Sorry. Okay, so a little bit about me. I'm from Shahola, Pennsylvania, United States. I graduated high school in 2024, and then soon after, the summer after, I started here at the University of Scranton studying computer engineering. Soon, a little later after that, I joined our amateur radio club here, W3USR, and started learning about amateur radio, and then a little bit after that, over the winter break we had, I started studying for my license, and then I got my license in January of 2025. After that, Dr. Frizzell had told me about this project, and I started working on it. Probably, it was around right the same time I got licensed. So with that, I wanted to do just a little background first on what HamSCI is. So HamSCI is a citizen science initiative that advances space physics research through the amateur radio community. It has three core missions, which are advancing scientific research and understanding through amateur radio activities, encouraging the development of new technologies that support research, and providing educational opportunities for the amateur radio community and to the general public. HamSCI brings together a wide range of participants, from backyard hobbyists to university researchers and professional space scientists, making it a truly collaborative and community-driven effort. For anybody that wants to look at it online, it's www.hamsci.org. There's a bunch of information on there. So who is behind HamSCI? I'm not sure if Dr. Frizzell told you guys much about this, but I figured I would touch on it. So Dr. Frizzell started HamSCI. I'm not sure the year, you'll have to forgive me, but it's led by him and the University of Scranton Department of Physics and Engineering, and then it's also in collaboration with Case Western Reserve University, the University of Alabama, NJIT or New Jersey Institute of Technology, Center for Solar Terrestrial Research, the MIT Haystack Observatory, and TAPR, as well as many volunteer members from the amateur radio community. Funding for this is primarily from the National Science Foundation, NASA, and the ARDC. So why amateur radio for space science? The ionosphere, which I'm sure most of you know, but that's the electronically charged layer of the Earth's upper atmosphere, which directly affects how radio waves travel. Amateur radio operators have long noticed that solar events like flares and geomagnetic storms can disrupt or enhance their signals. HamSCI turns those everyday observations into structured, reproducible scientific data, asking questions like how does the ionosphere respond to space weather inputs, what causes traveling ionospheric disturbances and sporadic E, or how do solar events affect radio propagation? So with that, I wanted to start getting in more centered on the project here by starting to explain what a personal space weather station is. So personal space weather station, or I also refer to it as PSWS, that's what it's commonly referred to, is HamSCI's flagship distributed instrument network. It's geographically distributed multi-instrument system for making ground-based measurements of the space environment. It is designed to be relatively low cost, anywhere from $100 to $1,000, to be deployable by citizen scientists, educators, and researchers. Data from individual stations is then aggregated into central research databases, which I'll get into a little bit more after this. Instruments include the Grape WWV Doppler monitors, WSPR receivers, which is, for those who don't know, WSPR stands for Weak Signal Propagation Reports. And then it also includes ground magnetometers. This is again led by the University of Scranton, and then it also partnered with TAPR, Case Western Reserve University, University of Alabama, NJIT, and then the MIT Haystack Observatory. So the Personal Space Weather Station is designed to use antennas to capture HF signals across the 0.3 to 30 megahertz range. So pretty much all of the HF range. I'm not sure what the band plan looks like in Africa where you guys are, but here that's around the whole band plan. The signals then are fed and mixed with a RX888 software-defined radio, which I have one in front of me here. I don't know how well you guys can see it. From there, it's connected over a USB bus to a... Sorry, there's someone outside the door. The RX888 is then connected via USB to a mini PC, which is running KA9Q radio and WSPRDaemon software to decode the signals that it's receiving. Also attached to that mini PC is a GPS-disciplined oscillator that ensures precise frequency timing. From there, the decoded data, which includes WSPR, FT8, and FT4 spots, is then sent to central aggregation databases. From there, it's sent to locations like PSK Reporter or WSPRnet, and then it's also sent to a local database stored on the Personal Space Weather Station. I'll explain that in a minute. After it's stored in the databases, it's used for both scientific analysis of the ionospheric conditions, and in this project's case, it's used for propagation insights for amateur radio and contest operators. So here is a physical picture of the Personal Space Weather Station that we use here at the University of Scranton. So it's the black box to the right of the picture is the mini PC. It's a B-Link computer. And then from there, it's connected to both the internet, and then it's connected over USB to the RX888, which is that middle box there. And then the GPS-disciplined oscillator is also connected to the RX888, as well as the mini PC. It's only connected to the mini PC to receive power, but I'll explain how you inject it into the RX888 in just a second here. But first I wanted to explain what KA9Q radio and what WSPRDaemon are for those who may not know. KA9Q radio is an open-sourced Linux SDR software developed by Phil Karn, also known as KA9Q. It uses fast convolution and IP multicasting to efficiently process signals from hardware like the RX888, which allows hundreds of channels to be simultaneously demodulated with modest computing hardware. This runs silently in the background as a Linux daemon, feeding process data into other applications, like WSPRDaemon. So WSPRDaemon is a robust Linux service that is used for decoding WSPR, FT8, FT4, FTS4W spots from SDR receivers. In our case, we're only using the RX888, but I do know that it works with other SDRs like the RTL SDR, smaller SDR receivers. This is capable of measuring Doppler shift while receiving multiple standard frequency stations simultaneously. And then it decodes what is received and outputs it. So this is among some of the top systems reporting globally, which collectively around 33% of the 7 million spots received at WSPRnet.org are decoded and received by both K9Q Radio and WSPRDaemon. So K9Q Radio basically handles the raw signal processing, and then WSPRDaemon handles the decoding and data reporting. So I also wanted to kind of explain how you would install a personal space weather station for those who may be curious. So right now, the operating systems that's being used is Ubuntu 24.04 long-term support, which is installed on that B-Link mini computer. From there, the software that's being used is K9Q and then WSPRDaemon, which both are installed and configured via command line. This has no physical graphical interface that's used on the mini PC. However, there are physical interfaces that I will show you guys in a little while here. Not for configuring, but for using it. So when you configure it, you set pretty much everything through the WSPRDaemon configuration file. You set things like your call sign, your grid square, the personal space weather station reporter ID, and which bands or frequencies you want it to monitor. Once the database is running, it is automatically uploaded to WSPRDaemon.org, WSPRnet.org, and the HamSCI personal space weather station database, as well as the local database that is installed for this dashboard, which I will explain in a couple slides here. So the system is always configured to restart automatically after power outages, and it is designed to run 24/7 for 365 days a year because signals never stop. So you want it to always listen. From there, I wanted to explain how you would modify the RX888. So I have a picture here. So if you look in the picture here, to get the precise GPS disciplined timing, you have to modify the RX888. So Tapper is the group that discovered and made a modification kit for this. So you add the external clock, and then you also add heat management to better, so that the board doesn't, destroy itself earlier. So when you get this clock kit, you take apart the RX888, just the outer shell, and then the whole board slides out of the shell. Inside there is, in the center of that picture, there's a little green jumper, which when the jumper is closed, which is what it comes as from the factory, it's using the internal clock. And then for our project here, you move that jumper to open so that we can use the external clock. And then right below that in the picture, there is a tiny little connector on the board that is then expanded out to a SMA for that 27 megahertz from the Leo Bodner GPS disciplined oscillator. And then when you go to put it back together, on the bottom side of the board, you put it's a thick thermal pad, probably about a 1/4 inch thick, that slides back into the case. And then there's also a new faceplate on the USB side. that right next to the USB, it will have a 27 megahertz spot for that clock signal. So from there, the mini PC BIOSes are set to have the fans on full 24/7 to eliminate any overheating concerns. And then, as I explained earlier, the AC power loss is also set to always on so that the system automatically restarts if the power goes out. From there, you would install Ubuntu 24.04, and then one important step is to disable Snap so that you prevent the unwanted automatic updates of software, because that could break things. And then it also disrupts the WSPRDaemon script. Finally, the WSPRDaemon configuration file is edited with all of the operator's information, like call sign, maiden, head, grid square, device IDs, and then from there you would run WSPRDaemon.sh-v, which would complete the installation. It also, it installs all dependencies, including KA9Q radio, so you don't have to figure out how to get them to talk to each other. It kind of just does it automatically. And then from there, you would run WD-A to start WSPRDaemon and then also enable it on boot so that it's running 24/7. Talked about that already. So I'm sure some of you may be wondering what antennas we're using for this project. So the main antenna we are using is the DX Engineering received short element active vertical antenna, which is a picture on the right that is installed at my house currently. And then it is run all the way back into my personal space weather station inside the house. The antenna we're using here at the station, which actually I would love to show you guys, but the monitor doesn't turn. I'm up in our W3USR amateur radio station right now. Here we're using an active magnetic loop antenna, which isn't really recommended anymore. However, it still works pretty much the same. We've just found there's better results with the active vertical antenna. From there, we also use the Leo Bodner LBE 1421, which has a frequency stability of its output, which is defined by the accuracy of the GPS satellite on board cesium frequencies and approaches around 1 times 10 to the negative 12, or that really small number of parts per million. This drives the clock on the RX-888, like I just showed you guys how to modify, which allows for the precise frequency measurements. Also built into WSPRDaemon is a KA9Q web, which is adjunct to KA9Q radio, and it displays the spectrum, waterfall, and other data from a personal space weather station receiver. It was originally created by John Melton G0ORX as a proof of concept design in late 2023, and has been significantly improved through collaboration through Scott Newell, N5 TNL, and Rob Robinette AI6VN, as well as Phil Carr KA9Q. It starts automatically with WSPRDaemon, and no additional or specific configuration is needed to get this running. When running it locally, you can access it at the personal space weather station's IP at port 8081, or when you're remote, you can do it via an SSH tunnel. I know personally this has been very helpful for us to see if the software is working correctly, to see if the RX888 is getting signals. So it allows the operator to visually confirm that the receiver is capturing signals. And then it also allows operators to check the band conditions at a glance and to see the real-time HF spectrum without needing to interpret command line output or raw data. So I have a photo here, but I also wanted to show live one of it. So if we go right here, can you guys still see my screen? I think so. Yeah. So this is installed at K3LR, which is out in western Pennsylvania. We went there over the summer and installed a personal space weather station, which I have some pictures that I will show as well for that. From there, I'll show a couple of photos here. So we went out there over the summer and installed both a ground magnetometer and a personal space weather station at the site. So here's just a couple of photos. This is also running the dashboard software. However, I'm not sure it's very used out there yet. But I'll get into that in a little while. Go back to the slideshow here. Okay, so from there, I will tell you guys a little bit about how the personal space weather station reports. So the big thing for this project is the personal space weather station local storage. So each decoded WSPR FT8 and FT4 spot is stored locally on a MongoDB database on the personal space weather station mini PC. Each database entry contains the call sign, grid square, frequency, band, mode, signal to noise ratio, drift, date, and time. This is absolutely foundational to the contesting dashboard, and a Flask app queries this dashboard or this database, in real time. From there, there's also upstream reporting. It's simultaneously uploaded to the WSPRnet.org, which is primary WSPR spot aggregation network, WSPRDaemon.org, which is an extended spot data including Doppler shift and noise measurements, and then it's also uploaded to the HamSCI personal space weather station database, where it's primarily used for scientific research and ionospheric analysis. These uploads all happen automatically and continuously, 24/7, 365 days a year. So what makes the WSPRDaemon reporting different than a standard WSPR receiver? It goes beyond the standard WSPR decoding by also reporting the Doppler spread and true signal strength, not just the signal to noise ratio. And then the noise measurements it makes also allow for diagnosis of site RF quality. From there, I will start getting into the project. So the personal space weather station so far has been very successful in scientific regards, but little work has been done to make it super useful and super useful. Yeah, I'll go with that. For real-time observations in the amateur radio community. So this project is designed to bridge the gap by building a contesting and dxing dashboard to run on individual personal space weather station nodes. A core objective of HamSCI is to equally benefit the scientific and amateur radio communities. And this has been a collaborative effort between the Frankfurt Radio Club, which they have provided many mentor volunteers, uh, a lot of contesting experience and project funding. It's obviously going to include the University of Scranton, which student researchers would be me, and then also my partner that is working on this project, Liam Miller, as well as the faculty like Dr. Frizzell. And then it's also been very collaborative between the HamSCI community. They've helped me with a lot of guidance and also to understand how the personal space weather station network works. So the contesting and dxing dashboard is a real-time web application using Flask, MongoDB, and Leaflet. It is primarily, the main program runs in Python. It's designed to visualize FT4, FT8, and whisper spots that are decoded locally. Right now, there are two primary views of the dashboard. One is an interactive map view, which personally I like better, however, some people don't, which shows band-specific, shows the spots in a band-specific manner using colors. And then there's also a regional band opening table, which displays the activity across 14 geographic regions across the primary contesting bands. So you could filter the spots by the bands, the mode, the country, continent, CQ zone, and ITU zone. This is currently installed at K3LR, like I said earlier, and it is also installed here at our station, which we have used it. The contesting team, we have used it during the ARRL single sideband DX contest in March of 2026, and they found it pretty helpful. So a little bit on the timeline of this project. So Dr. Frizzell came to me my first semester here and asked me, kind of introduced me to the project and what the project would entail, and I was pretty interested. So from there, we made a poster that was presented at the 2025 HamSCI conference, sort of as this is what the project is going to be, and to get feedback on what people thought of it and what they thought it should include. From there, I began the development of the dashboard majorly based off of the ideas from the 2025 HamSCI conference. The summer of 2025, I also installed it at K3LR as well as at my home for ease of development so that I wouldn't have to drive all the way to Scranton. It's about an hour drive for me to get here, so that makes that easier. From there, the fall of 2025, we had a working prototype. Don't have any photos of it, but it's nowhere near what we have today. So from there, we continued the development of the dashboard with feedback from the W3USR team as well as FRC. This has been presented to the FRC a couple of times, as they are the ones that are mainly giving all of the input towards it, and they're the ones funding it. So we try to keep them updated as much as we can. And then spring of 2026, around probably 3 or 4 weeks ago, this was presented at the 2026 HamSCI conference with a poster and as well as a live demonstration of it, which I will also be giving you guys a live demonstration of it in a little bit here. So from there, I wanted to talk about the requirements that we had come up with for this dashboard. So these were designed collaboratively through the FRC and the University of Scranton students and faculty with a goal of building a tool that answers the questions operators actually ask during contests and DX operations. So the display requirements include a real-time visualization, interactive world map using leaflet.js with band-specific colored markers and propagation path overlays, which propagation path overlays have not happened yet. However, that is currently being worked on by, like I mentioned him earlier, my partner Liam. Also, a regional band opening table showing activities across the 14 geographic regions and the main 6 contest bands. A big thing was filtering. We wanted the user to be able to select as much as they wanted, to show as many spots as they wanted, or to show only a specific region of spots. So these include the band, the mode, country, continent, CQ zone, and ITU zone. We also wanted it to include a configurable time window, last n number of spots, most commonly used is around 15 minutes. And then we also wanted to have an auto reload feature with an adjustable interval so that if you were using it during a contest, it would auto update for you. In terms of user experience, we want all of the filters you just set to save when you reload the page. So session persistent filters. There was something else I wanted to say, but it slipped my mind. So it'll come back and I'll mention it. A few more requirements. We wanted to answer key operator questions, which what bands are open and where, what is the maximum usable frequency or MUF, which band has the most activity, and what direction are the signals coming from. It needed to obviously integrate with the local personal space weather station receiver, with the FT8, FT4, and whisper spots. And then also we wanted to, at some point, connect it to external space weather data sources. Yeah, that hasn't happened yet, but we're working on it. So how does the dashboard work? A WSPRDaemon config command is used. So when you're configuring the system, there's also a line in here that we had added to the system where it runs every time the WSPRDaemon session, every time WSPRDaemon decodes something, it instructs it to store it in the local database. So for Whisper, that's every 2 minutes. Every 2 minutes, a script is run on each personal space weather station, which collects the spots and stores them in that MongoDB. And then the same thing happens for FT4 and FT8, just on a shorter time span. I believe it's every 15 seconds. From there, a background program written in Python continuously is parsing each database entry and exposing the data to a REST API in JSON format, which shows the call sign, grid square, frequency band, and more. All the important information to make it visible on the map. From there are 2 APIs that are currently in use to serve the different dashboard views. The map and the table require similar data structures, but they're slightly different. So for easy use, there's two APIs. The map API, which feeds all of the data to the leaflet.js interactive world map, and then as well as the table API, it feeds the spot data into the regional band opening map. There's a web application that is also built on top of this to simultaneously pull from both APIs at the same time to render both the table and the dashboard and the map in one view. From there, so this is what the map looks like. And so as you can see up top, there is all of the filters that are available, as well as the mode selector. Now, one thing I should note, this site here, UACNJ, now that is I would say the main production site for this project. That is a personal space weather station receiver down in Jenny Jump State Park down in New Jersey, which is in Hope, New Jersey, for those who want to look. I have remote access to this system, so this system is constantly being updated with the dashboard, and it is also published to the internet for anyone to go look at uacnj.kd3ald.com. I'll do a live demo of this in a second, but I want to show you guys the map or the table view as well. So, as in addition to the map, we have this table. Now, this is sort of designed off of what the FRC has taught me. So, some of their members use Excel spreadsheets to sort of map spots. So that was the main idea for this. It works the same as the map in terms of receiving spots and number of last spots, but from there it's a little different. So there's a configuration file that is in the code for this dashboard that allows you to set what bands you want it to, filter by. So for me, mainly right now it's set as the 6 major contest bands in the United States. This in the future will be user configurable online, but we just haven't gotten to that point. And then these are also, there's 14 geographic regions here, which will also eventually be user configurable, but these are the 6 main ones that the Frankfurt Radio Club had set as, I would say, maybe the most important. Now, you may notice all the boxes right now are green. So there's a line up at the top called green threshold. So you could set that number to whatever you want it to be, and that would be considered, quote unquote, a good location to go try and talk to. I haven't used this part of it, but I know some people that have, and they say it's pretty useful. So from there, let me pull up the dashboard here. So you guys should be able to see that. I will update it here. So this is the map. So let me scroll down just a little bit here. I'll get some more spots on there. We'll say for the last 35 minutes. So we have many filters for the bands. So in terms of, band filters, we have all of the bands so you can see everything. And then there's also just the contest bands, which is those 6 major contest bands. And then all of the different bands, aside from 70 centimeter, because I don't think I've ever seen one of these on 70 centimeter. From there, we have country filter, which is just all of the, I would say the ones that stand out the most, at least, or these are what the FRC had requested be put on here. There's continent filters, which we could do that. I would do Africa, but I don't know if it'll work. It should. Yeah, there's one. I'll go back to all of the continents. Sorry. A big thing. I'm not sure if you guys have used it a lot, but CQ zones is a big thing in contests here, as well not as much, but ITU zones are also important. So we added a CQ zone filter, and as well as an outline. So you can see all of the CQ zones live on this map. And then we did the same thing for ITU zones. You can see all the ITU zones on the map. Next to that, we have the auto reload feature, which right now there's options for how often you want it to reload. From there, I will scroll down and I will show you guys the map, or not the map, I'm sorry, the table. Say I set the green threshold to 100. So I wanted there to be at least 100 spots before I set that as good. So I would say the green threshold is 100, and as of right now, there's only 100 plus spots in North America for this personal space weather station receiver over the last 35 minutes. Let's see. So if you could see here, there's the 6 major regions, and then there's the unknown. So every so often we get spots like the one on this map here, and I believe that's region 87, that is just out in the middle of nowhere. So occasionally we get those spots, and that is classified as unknown. So it goes in the unknown category. As well as sometimes I have found some issues where some spots appear off the coast of the United States, so they also may not map well, or the table may interpret them as being in different zones. So those also go in the unknown category. From there, I think I will go back to the presentation here. Okay. So the current status of the dashboard, a working prototype is live at uacnj.kd3ald.com, which anybody is welcome to visit if they would like and try out the dashboard for themselves. As I mentioned earlier, this was used in the ARRL single sideband DX contest in March of 2026 here. Both of the map and table views are fully operational with that real-time spot visualization, as well as all of the band mode filters and filters like that. So in terms of installations, this has been installed at K3LR, Whiskey 3 Uniform Sierra Romeo, and then it's also been installed at Dr. Frizzell's house. So that one's not operational yet, and then it's also been installed at my house. In terms of development, the core data pipeline is complete. from WSPRDaemon to MongoDB to the REST API to the web app, as well as that two API architecture serving both the map and the table. And then all of the code for this is open source and publicly available on the HamSCI GitHub. It's called FRC Contesting for those who'd like to look at it and kind of explore it more. From there, I will talk about some of the future work. So in the future, we aim to add alerting functions to notify operators of specific band openings. So ideally, the contest operator could say, let me know when band openings to Europe are on the 20-meter band. And that would kind of run in the background of the dashboard and then alert the user when that happens. We also want to integrate with external propagation sources like ITU-R, HF, which Liam has a working prototype of actually, so that should be integrated fairly soon for those of you that are interested in that and want to see that. We also eventually want to integrate with the N1MM Plus logging software for easier contest use. From there, that I feel like that is like our next major milestone, in my opinion, in terms of contesting. That would allow the user to. I just saw that chat. I'll post it in just a second here. The link of the GitHub, if I could figure out where the chat is. So from there, we want to also have a relatively large system, like Whisper.rocks. I'm not sure if anybody has used that. I will also show that in a second, to support multiple simultaneous personal space weather stations for broader propagation comparisons, and then a better session persistent filtering system, because right now that's not currently working, so that when users leave the page and come back, they still have their preferred configuration. We also want to install and test this at more volunteer contest stations so that we can have more operator feedback on the design, so that we can then incorporate that into the next iterations of the dashboard. We're going to continue using it here and testing it during the W3USR contests. And then the scientific contributions. We want, ideally, this should help expand the personal space weather station network across North America, as it makes it easier to visualize the data of that your personal space weather station is decoding, as well as we want to contribute to a broader understanding of localized and global HF conditions and strengthen that bridge between the amateur radio operation community and then the space weather research community. Oh, sorry. Let me pull up Whisper.rocks here. So this was sort of the, I would say, start of the project. This was what we used for inspiration. So as you can see, it's kind of similar to the dashboard I have developed. However, they're different in their own ways. So this was something we had just, sort of thought of, or well, Dr. Frizzell had known of this website and said I should look into it and try and develop something off of this. So this was the sort of inspiration for it. So another, oh, sorry, I hit the wrong button. Another sort of thing about this dashboard is it is designed to be fully offline. So you don't need any internet connection or anything like that to get the dashboard to work once it's installed. You need it to pull it from the GitHub and everything, but in terms of the map is fully offline and can be rendered locally, as well as that's the point of the local database, so that it doesn't need to pull from the internet. So with that, I realized that was probably a lot of confusing and not in order information, so I apologize for that. But with that, I'd like to say thank you.